Welcome back to JVM Internals Crashcasts. I'm your host Sheila, and today we're diving deep into the fascinating world of memory barriers and the happens before relationship. We're currently in level 2 of our series, exploring the JVM memory model. Victor, are you ready to unravel this complex topic for our listeners?
Absolutely, Sheila. I'm excited to tackle this crucial aspect of JVM internals. It's a topic that often confuses developers, but understanding it is key to writing correct programs that use multiple threads.
Great. Before we jump in, listeners, make sure you're familiar with basic concurrency concepts and the JVM memory model we've discussed in previous episodes. Now, let's start with a quiz question to get your gears turning. In a multi-threaded Java program, if thread A writes to a shared variable and thread B reads from it, under what circumstances can we guarantee that thread B will see the updated value?
Oh, that's an excellent question, Sheila. It really gets to the heart of our topic today. Listeners, take a moment to think about it. Consider what you know about threads, shared memory, and synchronization. The answer might not be as straightforward as you think.
While our listeners ponder that, let's start with the basics. Victor, can you explain what memory barriers are and why we need them?
Certainly. Memory barriers, also known as memory fences, are low-level synchronization mechanisms. They ensure specific ordering guarantees for memory operations. In modern computers, both hardware and compilers can reorder memory operations to optimize performance. While this is generally beneficial, it can lead to unexpected behavior when multiple threads are involved. Memory barriers prevent certain types of reordering, ensuring that memory operations are visible to other threads in a consistent order.
That's interesting. So, it's like putting up traffic lights to control the flow of memory operations between threads. Can you give us an example of when this might be important?
Great analogy, Sheila. Let's consider a simple example of a multi-threaded bank account. Imagine thread A is depositing money while thread B is checking the balance. Without proper synchronization, thread B might read an outdated balance, even if thread A has already made the deposit. Memory barriers help ensure that thread B sees the updated balance after thread A's deposit.
That makes sense. Now, I've heard there are different types of memory barriers. Can you elaborate on that?
Absolutely. There are typically 4 types of memory barriers. 1. Load barriers. Ensure all loads before the barrier are completed before any loads after the barrier. 2. Store barriers. Ensure all stores before the barrier are completed before any stores after the barrier. 3. Load store barriers. Ensure all loads before the barrier are completed before any stores after the barrier. 4. Store load barriers. The strongest type, ensuring all stores before the barrier are completed before any loads after the barrier. In Java, these are often handled automatically, but understanding them helps grasp how synchronization works under the hood.
That's quite a bit to take in. How does Java handle these memory barriers for us?
Great question. Java provides higher-level synchronization tools like synchronized blocks and volatile variables. These automatically insert the necessary memory barriers. For example, exiting a synchronized block acts as a store barrier, ensuring all writes inside the block are visible to other threads.
Now, let's talk about the happens before relationship. How does this tie into memory barriers?
The happens before relationship is a key concept in the Java memory model. It defines when the results of one action are guaranteed to be visible to another action. Memory barriers are the behind-the-scenes mechanism that enforces this relationship. For example, if action A happens before action B, then the results of A are guaranteed to be visible to B. This is crucial for understanding how concurrent programs behave.
That's fascinating. Can you give us a concrete example of the happens before relationship in action?
Sure. Let's go back to our bank account example. If thread A releases a lock after updating the account balance, and thread B subsequently acquires the same lock before reading the balance, there's a happens before relationship between these actions. This guarantees that thread B will see the updated balance.
I see. So, what are some common pitfalls developers should watch out for when dealing with memory barriers and the happens before relationship?
One common pitfall is assuming that all operations are automatically visible to all threads. This can lead to race conditions, where the outcome depends on the timing of thread execution. Another is overusing synchronization, which can harm performance. It's crucial to strike a balance between correctness and efficiency. A tip for our listeners: always use proper synchronization when sharing mutable data between threads. The synchronized keyword and java.util.concurrent utilities are your friends.
Those are great points, Victor. Now, let's reveal the answer to our quiz question. In a multi-threaded Java program, if thread A writes to a shared variable and thread B reads from it, we can guarantee that thread B will see the updated value if there's a happens before relationship between the write in thread A and the read in thread B. This can be established through proper synchronization, such as using volatile variables, synchronized blocks, or other concurrent utilities that provide visibility guarantees.
Excellent explanation, Sheila. Understanding these concepts is crucial for writing correct concurrent programs in Java.
Indeed. To summarize today's episode: 1. Memory barriers are low-level mechanisms that ensure ordering of memory operations. 2. There are 4 types of memory barriers: load-load, store-store, load-store, and store-load. 3. The happens before relationship defines when the results of one action are visible to another. 4. Proper synchronization in Java establishes happens before relationships, ensuring visibility of shared data between threads. 5. Always use appropriate synchronization mechanisms when sharing mutable data between threads to avoid race conditions and ensure correct program behavior. In our next episode, we'll be diving into the fascinating world of garbage collection algorithms. Don't miss it.
I'm looking forward to it, Sheila. Garbage collection is another crucial aspect of JVM internals that every Java developer should understand.
Absolutely. And to our listeners, if you've enjoyed this episode, please subscribe to JVM Internals Crashcasts and leave us a rating. Your support helps us continue creating in-depth content on JVM internals. Until next time, happy coding.